Today we're going to take a look at angles. We're going to talk more about angle measures, how angles are related. The actual title of this is more about angles, so that's very, enlightening, isn't it? More about angles. So the first kind of angles we're going to talk about are called vertical angles. Vertical angles are pairs of angles that appear across from each other whenever two lines intersect. So can somebody give me an example in this diagram using the correct, ordering of letters and so forth, of one pair of vertical angles, angles that appear to be across from each other? AED and AEB. And what was your other one? So these two angles are the ones that Jacqueline mentioned. Do you guys agree? Yeah, that's exactly what a pair of vertical angles would be. And there's another pair of vertical angles as well. There's this pair over here, right? So marking them, and we would have A, E, B, and what's the other one? B, E, C. And you'll notice big, bold type, underlined and everything at the bottom. It says vertical angles are congruent. And I'm actually going to justify to you why that's true on the next slide as well. So the fact that I've sort of marked them with these congruency sort of markings is not by accident. So let's actually take a look at why this works. And we're going to reference back to this diagram. So if you have this diagram, hang on to it, or at least flip back and forth. But I would like to number, no, I don't think I will. I don't think I'll do it that way. I was thinking I might number my angles, but I think we'll just leave them like they are. What I'd like to do first is I'd like to take the two angles that are along the top. Angle AEB, that was the first one that Jacqueline mentioned. And I would like to take the other angle along the top, which is BEC. And I'd like to add their angle measurements together. Okay, I'm not adding the angles together. You can't really add angles from what we've done so far, but you can add the measurements, right? I could add the degrees. So if one of them was 50 degrees and the other one was 75 degrees for two angles, I could add those numbers together. Notationally, what that looks like is we put that M in front. Do you guys remember us talking about that last time? M means how many degrees are in the angle. So if I were to add those two angles together, this picture over here, what would you equal? You would equal 180, exactly. Okay. Next, I'm going to do one more of those. I want to add the angles together that are on the top and on the left. Okay, so that same angle AEB, and then the other angle is this angle AED. So I'm going to write down one more sort of equation. Still AEB. And I'm going to add to it the measure, which is measure of angle, what was in our picture, AED. And what do those equal? Those also equal 180. And I should have put my degrees on there, so make sure that you go back and grab that degree measure. I didn't do that. 180 degrees. So far, so good? Okay. So I contend if these two angles, I had them up here. If these two angles equal 180 and these two angles equal 180, then if I were to put them together, they add together, they're the same. So if they both equal 180, they equal each other. Okay, so let me actually mark it on here so I can say it in sort of print. If this one equals 180, and this one equals 180, then I could actually set those equal to each other. So blue box equals red box. So that's my next step. I'm going to write down the measure of angle AEB plus the measure of angle BEC equals the measure of angle AEB plus the measure of angle AED. If they both equal 180, they equal each other. Make sense? Okay. What do you notice on the left-hand side and on the right-hand side of this? They both have AEB. right? This is algebra, right? If I have the same thing on both sides, I could subtract it. It's just a number. I know it doesn't look like a number, but once I put the m in front of it, it means it's a number. It's the angle measure. It's just an angle measure. So I can subtract that. I can subtract the measure of angle AEB. And what will I be left with when I do that subtraction?
Measure of angle BEC equals measure of angle AED.
So if you go back to the picture, BEC and AED were these blue ones that I marked, right? They're congruent. It's very straightforward argument as to why it works, but it's very, very kind of elegant almost. It works very, very nicely. All right, we're going to look at some more in terms of our angles. So our next one we're going to look at are complementary and supplementary angles. So complementary angles are angles whose measures add up to 90 degrees. We will talk about these as angles complementing one another. And then supplementary angles are angles whose measures are adding up to 180 degrees. So here's what I'd like for you to do. I would like for you to write down with the pictures given, okay, the top picture is the picture for the complementary, the bottom picture is the picture for the supplementary. I would like for you to write down one pair of complementary angles. There's lots of them, so just write down one pair of complementary angles. And then in the second diagram, I'd like for you to write down one pair of supplementary angles. Just one pair. Okay, pick your favorite. And once you have, I want you to exchange papers with someone else and see if they agree with yours. Yours may match theirs and it may not, but see if they agree that you found one pair of each of those types of angles. Once you've written one down, swap papers with someone near you and just have them look at what you chose. And you look at what they chose, okay?
Because if you did like COD, you can see that one's not even like 90 degrees. And then AOB is also an acute angle, so those two together will add up. Okay. Yeah. Okay, thank you. You're welcome.
Okay. Is it coming back to you? Did you find a pair? Okay, so I'm going to have you guys give me an example of a pair. So, Emma, can you give us an example of what you did for complementary?
Measure of angle AOC and measure of angle COF.
And if we're looking at angles, we don't have to say measure of. We could just say the angles. It was COF. Okay, so do you guys agree? Does AOC and COF work? Yeah, very good. All right. Kaylee Bryant, what did you get on your supplementary angles?
A
Okay. And what's your other one?
And then the other one would be VOC.
AOC and BOC?
Yeah, VOD.
BO, I think maybe COD.
Oh, yeah, C.
Is that the one you want?
Yeah.
Okay. Yeah, so angle AOC would be this one right here. And then COD would be this piece right here. Okay. Does everybody agree with that one? Excellent. So those are supplementary angles. Very nice. All right, another type on angles, another piece of description for angles is we're going to call something a transversal. So if we have two lines, sometimes they're parallel, but they don't have to be. But we have two lines and they're cut through by a third line. That third line, it's called T here, is a transversal. It's just the line cutting through the other two lines. Okay? So the T here is the transversal that it's talking about. The lines do need to lie in a plane. You know, the two lines have to lie in a plane. But we have a T, a transversal cutting through them. Now, a lot of the times, and in the most helpful and pretty diagrams we have, they are going to be parallel, right? Line L and line M are parallel. But they don't have to be for T to be a transversal, okay? So that's sort of a misconception that we sometimes have because so often they are parallel, we just assume they always are, and they don't have to be. All right, when we have these two lines that are cut by the transversal T, they create some different types of angles. The first type of angle that we're referencing is something called an interior angle. So the interior angles means that they need to be in between the two lines that sort of appear to be parallel, okay? So they're in between these two lines. So can somebody give me an example, looking at this diagram, and they are labeled with numbers, give me an example of an angle numbered, or a number of an angle that's in between, that is an interior angle. 8 would be one of them. Give me one more. 3. So what are the other two? I'm not going to write them down, but yeah, 7 and 2. So there are 4 interior angles, all 4 of those that are in between the lines. Alternate interior angles means that it's a pair of angles that's in between the lines and on opposite sides of the transversal. So if we use angle 8, what would be its alternate interior angle? 2. Okay, we only have 4 angles to choose from. I've already picked 8, so you're down to 3 choices. It's like multiple choice, right? Has to be on the opposite side of the transversal and non-adjacent. That makes it angle 2. Okay, and then 7 and 3 are the other pair. Exactly. So we have pairs 8 and 2 and pairs 7 and 3. We don't just have interior angles, we also have exterior angles. Exterior angles are angles that are on the outside of the transversal. So somebody give me an example of an exterior angle. 1. Give me one more. Not 2, 4. Somebody said 4. Yeah, 4. And then what are the other 2? 5 and 6. So they're the angles that sort of appear to be on the outskirts of things, or on the outside of what's going on. We can also talk about alternate exterior angles, just like we talked about alternate interior angles. They have to be non-adjacent, so they have to be not next to each other, and they have to be on the opposite side of the transversal. So if I started with angle 1, what would be the opposite, or the alternate, rather, exterior angle? It would be 5. And what would be the other pair? 4 and 6. Okay, is everybody good with that? So visually we're talking about these 2 objects here. Okay, I think this is our last one, corresponding. Corresponding angles, yes, are angles that are in the same position where the transversal intersects one line as it intersects the other one. So, somebody pick any of, there's 8 angles here. Somebody pick me an angle. 4, okay. Here is angle 4. Does anybody know what the corresponding angle would be for angle 4? It would be 7. Very good. They're in the same position along the line, along the transversal line, and the intersecting line. So angles 4 and 7 would be at one example of corresponding angles. Just for fun, let's write down one more. What's another pair of corresponding angles? Any pair you like. What was it? 8 and 5. Do you guys agree? Looks good to me. 8 and 5. So it's this one and this one. Any idea what amazing thing happens if corresponding angles are congruent? Do you know? What would happen?
The
Hmm?
ones on the opposite side would be congruent as well.
All right, so let's say, for instance, just because I've already got them marked, those black angles, the ones that are 4 and 7, let's say angle 4 and angle 7 are congruent. Then what would you be able to tell me about 5 and 8? They're also congruent to each other, not to 4 and 7, right, but to each other. What would that make true about 6 and 3?
They would be congruent to 4.
They would be congruent to each other. And then and they would also be congruent to 4 and 7, that's true. But they are automatically because they're vertical. How about 2 and 1? Same thing, right? So you'd end up with all 4 pairs that are congruent. All it takes is one pair to be congruent. There's something else then that's sort of super nice and magical that happens if we do have this congruency relationship going on. If we have that relationship, it actually means that the lines are parallel. And that's a two-way relationship. If the lines are parallel, then we have these congruencies. And if we have these congruencies, then the lines are parallel. And I believe that that's actually happening in the next couple of slides, and we're going to write those details down. So what happens if these alternate interior, or if these corresponding angles are congruent? Well, what ends up happening is, we kind of said it, but the alternate interior angles are also congruent. And the alternate exterior angles are congruent. This is what you guys did with me. You went all the way around this image and you kept telling me all these things that are congruent, right? So over here, this angles here and these angles here are congruent, and they're congruent to the ones that are opposite them because they're vertical angles, right? And the vertical angles, we showed why that works. And so now all of a sudden, alternate interior angles 7 and 3 are congruent because they're both marked in black, correct? And alternate exterior angles 4 and 6 are congruent because they're also marked in black. And our pair of lines is parallel. Okay, so let's summarize what all that did. I said it out loud already, but if we have two distinct lines in a plane and they're intersected by a transversal, we know that the pair of corresponding angles, alternate interior angles, alternate exterior angles, are congruent if and only if, what? The lines are parallel. This phrase, if and only if, is what we use in mathematics to mean that the direction goes either way. We can either start with the stuff about the angles and end with the stuff about being parallel, or we can start with the information about being parallel and end with the information about congruency of angles. The direction goes either way. See, that doesn't always work. It doesn't always work when we're using English to describe things. Let me give you an example. Okay, I'm not going to be able to come up with it on the spot. There we go. I know what I wanted to come up with, but it wasn't working in my mind. I'll think of it later. We are going to construct parallel lines next using a triangle. So this is the first piece of where I'm going to pass out some information, some papers, or not papers, but some protractors if you don't have one. You just need a straight edge. I'm going to pass out the straight edge. I'm just going to pass out the protractors. So if you already have a protractor that's got the straight edge on it, that's fine. If not, just grab one of these. And I'll just pass them around. we're using the straight edge part of it, not really the protractor part of it. But what I'm going to show you is actually described on page 659 as well. And what we're going to do is we're going to start with a triangle, right? And our triangle is going to have points A, B, and C on it, and it doesn't really even matter. So you can pick where your A, B, and C are. Just draw them on your paper. And we're going to label them the same, though. We're going to put the A and the B along the top and the C along the bottom. And you can connect them to form your triangle. That was not what I meant to do. Let me try that one more time. That's better. Okay, so you've got a triangle. Okay, so everybody has a triangle, right? C's at the bottom, A and B are along the top. And what I want you to do is I want you to take your protractor and I want you to line it up alongside AC. Okay? So visually, here, let me use this. So the straight edge of your protractor is going to be lined up alongside AC. And it's going to extend up here further, okay? But it's going to be along this line. I would like for you to put anywhere above points A and B, another point, and we will call it, I'm going to use what your book does, they call it P. Okay? So somewhere, if you will, up in the air. All right. So I'm going to use a red straight edge. So this is my protractor straight edge, if I can draw it straight. I think I got it okay. It's lined up along the side of it. Okay, so imagine I've got my protractor sitting over here. That's the image you have, okay? So what you're going to do physically next, what you would do, is you would actually physically move the triangle up. You can't do that because you sort of drew it, right? But can you imagine doing that? If you had a little piece of paper that you cut out to be the exact same size as the triangle, and you slid it up so that at the side AC was still on the red line I've drawn above. You're sliding it. And you're sliding it up until it hits point P up in the air somewhere. Okay? So physically on my screen, I think I actually might be able to do that. I'm going to try. And I'm going to slide it until it hits, in fact, let me do one more thing. I'm going to extend the line for AB to be longer. Otherwise, it won't actually hit point P for me. Okay. Okay, I think that works. So I'm going to slide this image up along my line. Okay? Those two edges still have to be along the red line, right? And I'm going to slide it until I hit point P. So here's where it was originally, and then I slid it. Are you guys with me? Took the image, I made a copy of it, and I moved it along the edge upwards. Okay? What do you think this created? That point P shouldn't really be there anymore, or still yet, because it wasn't down here to begin with. What did I create when I did that?
Parallel line.
I created parallel lines. So what this actually is this is an old carpenter's trick. So carpenter wants to be able to create parallel lines. How could they do that easily? Well, they've got all sorts of measurement tools with them, right? So they could take that straight edge and they can create a triangle that hits what they want to do. Okay, it hits these particular points. We need all 3 points of the triangle for this to work, though. We actually need the points A and C because they lie along that red line that is my straight edge. And we need that point B in order for it to actually create the line that we're moving to create the parallel line. So we actually end up with, we'll call them, give them names, I didn't label them yet. This point, we'll call it A prime because I moved it. It's the new location of where point A would be. And then what ends up happening is that A prime P, which is a line, right, is parallel. There's two straight lines. They should look straight. They look a little bit frumpy. It's parallel to line AB. This also creates some congruent angles, right? That's actually how we know that the image is parallel lines, is because we used the same triangle to slide, which means this triangle down here has this angle right here at B. It's congruent to this, I'm sorry, at B at A. This angle right here at A that's congruent to this angle at A prime, because it's the same triangle, right? So I know those angles are the same measure. I created it. I shifted it, but it didn't change size. So because I have congruent corresponding angles right here and here, I know I have the parallel lines that I was shooting for. So that's kind of cool, right? It's a cool way to do something that is very tricky to do if you were just trying to draw it freehand. It'd be very difficult. All right, here is our next fun activity. Are you ready? Everybody needs a sheet of scratch paper. So take a sheet, pass it around. It's all scratch paper, so we can just throw it away when we're done. We're going to need those straight edges. Okay? So grab that straight edge. And you're going to create, well, let me write this in and then we're going to create it. You guys tell me, what is the sum of the measure of the angles of a triangle? You know the answer. What is it? It's 180 degrees. So we're going to look at the y, and this is an example that I have done numerous times. It works so very wonderfully well. I want you to take your sheet of paper, and I want you to put 3 points on the paper. Don't make them tiny and super close together, but don't take up the entire paper either, because we're going to use the paper for one more thing. So think about, imagine you're using about half the sheet of paper. So does someone have an extra sheet of it that I could use? I should have kept one for myself. I'm sorry. 3 points. Any 3 points you'd like. Okay, so you're going to create points maybe. Okay, so here are my 3 points. Okay, your 3 points are not going to look like mine. Then they shouldn't. I don't want you to think that there's something magical about the 3 points you picked, because there's not. Next thing I want you to do is take your straight edge, and I want you to connect the 3 points. And what shape are you going to be creating? A triangle. Fantastic. All right, so take your straight edge, make yourself a triangle. I'm going to make it 2 just for fun. And then on the inside of the triangles, angles, I want you to number them 1 to 3, or A, B, C, or whatever letter. Something that distinguishes them apart from one another, but make it on the inside. Okay. So this is my triangle. Does everybody have a triangle with the angles on the inside marked? Got to be on the inside or it's not going to work. Okay? All right. Next step. You need to cut out your triangle. I just have a bag of goodies today, don't I? Mm-hmm. All right. So I don't have enough triangles. These are old school scissors. I remember these scissors from when I was a little girl. That's how old school they are. Okay. I have one. So cut out your triangle and then pass the scissors to someone else. I'll do the same. Try to keep it as close to your lines as you can. The argument here will just so much nicer if we're careful. Everybody have, or we're getting close, and not everybody does, because we're still passing around scissors. Did we get it all? Did you guys get yours all done? No? Oh, sorry, I see it. Abby still has it. Okay. You're all appreciating the good scissors that you've life, aren't you? Yes, I know you are. For those of you who are sort of waiting at this moment, what you're welcome to do on the other half of your piece of paper, because we're going to do it next, is to do the same thing with 4 points, okay? Don't make the 4 points anything super specific, okay? So I'm not saying create a square. Just make 4 points, it doesn't even matter if they're concave or convex when you attach the lines to them. It really doesn't. But make yourself 4 points as well, and then connect them with the line segments, and then we're going to label on the inside. We're going to cut them out. Super tiny diagrams are not going to be as easy to work with. So if you make them with a little bit of size, that'll help. So like this is my shape. You're creating a quadrilateral. It doesn't need to look anything specific, and it certainly does not need to look like mine, okay? But you've got 4 vertices, and you're going to label the vertices 1 through 4, or A through D. And then once the scissors find you again, cut that image out too, okay? So we're going to have a quadrilateral and a triangle that have been cut out when we're done. Is everybody almost to the point to have your triangles cut out? Whoever has the scissors, once you're done with the triangles, go ahead and cut out your quadrilateral, and then pass the scissors kind of back through the people again. And then everybody else can cut the quadrilateral. Huh?
Is that okay?
Yeah, it should still work okay. You can measure, you can do it that way. Yours is convex or concave, that's okay. Yeah, that'll still work. And you're all going to make sure that the trash goes in the trash can when you leave, right? So I don't have to come around and find all the squares and the scraps of paper. That'd be awesome. Yes, once you've cut out both your shapes, you're done with it. I had no idea you were going to cut paper in math today, did you? What fun. Okay, is anybody waiting on scissors still? I see Jacqueline has a pair. that paper today, but you know what you're about to get to do? Rip paper. That's exactly right. That's the next thing you're gonna do is tear your pieces of paper up. What? Yeah, I know, for real. All right. Don't tear anything yet. There's some specific instructions about how tearing the paper works. Does anybody else need scissors? Okay, so we're getting close. All right. Take your triangle. And you're going to tear apart your triangle into 3 pieces. The 3 pieces need to have angles in each of the pieces. So you're going to rip it for your angle 1. You're going to rip apart angles 2 and 3. So you have 3 little pieces of paper. I'm pretty sure this is going to work for your quadrilateral that you just made just a minute ago there, Elena, but maybe it won't. We'll see.
Yeah, I have a bad feeling on this one.
I'm not sure if it's going to work with the convex one or concave one. But. All right, the next thing you're going to do is you've got these black edges along 2 of the 3 sides of the torn pieces, right? You guys see that? So the angle measure, angle 1, needs to line up alongside the angle measure for angle 2. The sides need to match up, and then the side measures for angle 3 need to match up. I need them to lie alongside each other. So if you take 2 of them together, the vertices should be going beside each other, and their side lengths, the rays that would have extended, need to go beside each other. So it would go like this. And then do the same thing with angle 3. Yeah, you got it there, Skylar. It doesn't matter. It doesn't matter the order you put them in. That makes no difference. But you should have them vertice to vertice, side to side. Got it? Yep. It's got to be, the vertices have to be in the same place. So A to the A, B to C to A, the 1 to the other have to touch each other. There's A and here's
So it's
B.
like on a straight line? I mean,
Is that what happened, really?
a line, not a
No
straight
way!
line.
Is that really what happened? To yours too? Oh. Did everybody's do that? Oh. Oh, where'd it go?
It was right there.
It was right there. Getting close to 100% Whitley. How many degrees are in a line, a straight angle? 180. And what did this just make? A straight angle, 180. That's the simplest way that I know to talk about why the angle measures of a triangle add up to 180. So, you now have a quadrilateral, right? You tell me first. We'll fill it on the next slide. How many angle measurements are there, or what's the sum of the angles in a quadrilateral? Does anybody remember? It's 360, yeah. And we're going to do the same thing, the Y. So take your quadrilateral. I'm not sure about Elena's quadrilateral. We'll see. Did anybody else have a convex one like Elena did? Kaylee does. Anyone else?
It does work.
Okay, I thought it would, but I haven't actually done it with a convex one. Tear it apart. So you should have 4 pieces. Your angles should be the 4 of them. And you should match up all of those together the same way you did with your triangle. All the corners should be matching up. So column 1, 2, 3, 4.
I didn't think it would work either of those.
That's it.
One.
Very nice. You're fine. These have to be matching up along the sides here. They all have to go together, just like the ABC was here.
Oh.
Here. There. Do you have, yeah, you have yours over there now. All right, I think I checked everybody's. What happened? It connected, right? Completely and totally. And if we had the image right of our shape, it would make a circle, right? Or it makes the center of the circle, I guess you could say, or something like that. And how many degrees are in the center of a circle? 360. So we have 360 degrees in our quadrilateral. Unfortunately, a pentagon, when we start trying to do that, will begin to be, that's the first polynomial, or polygon, excuse me, that we have that will be more than 360, which means it starts to overlap itself, and we can't sort of just visually see it quite as well. But what we can do is we can notice a few things. So if you notice, if I were to take my quadrilateral, so here's an image over here of a quadrilateral, ABCD, and I could split it into two triangles, right? And if I had two triangles, how many degrees are in each triangle? 180. And what happens when I add 180 and 180? I get 360. So what do you suppose might happen for my pentagon? So do you know what that value is? 180 plus 180? It's 1, yeah. And another one is 540. And again, the image of taking my pentagon and splitting it into three triangles, right? You do have to split them from the same corner for this to sort of start to make sense. You can't sort of just decide you're going to willy-nilly split them somewhere else. That's not going to work. But you end up with 540. So the pattern, what about a hexagon? What do you think is going to happen for our hexagon? What is it? 720? Where's my notes? Put them away. No. Okay, so what's the pattern? Well, if I take they're adding 180 each time, right? That's what we call a recursive pattern. We do that in proportional statistical reason. No, we do that in number theory. It's where we talk about recursive patterns. So recursive pattern means you're seeing, if you start somewhere and you know the pattern, you can create the next object. So if I asked you about a decagon, 10-sided figure from the hexagon, you'd have to figure out first the 7-sided figure, and then the 8 one, and then the 9 one, and the 10 one if you're thinking about a recursive formula. So there's another way to do a formula for that, and that's to actually put what we would call an nth degree, or an nth formula, or a general formula, which we do in that particular class as well. We're going to talk about it a little bit differently, but it's going to have that same sort of a feel. So if we take the number of triangles, how many triangles did we have? Let's go back and do that. Well, one triangle is just one triangle. How many triangles were there in a quadrilateral? There were 2. 4-sided figure, 2 triangles. How many triangles were there in a pentagon? 3. How many triangles do you see over there in that hexagon?
4.
So what's the relationship between the number of triangles and the shape? It's number of the sides minus 2. So the number of triangles is the number of sides minus 2. So the sum of the measures of the interior angles is the number of sides minus 2 times what? 180. And if we call the number of sides n, then we could shorten this sort of description down to say that it's n minus 2 times 180. Couldn't we? Yeah, it's a lot easier to write it that way. All right. So what would we have as the sum inside of a 37-sided polygon? What would we get?
35
So 37 minus 2, which is 35. And then what would we do? Multiply by 180. So 35 times 180. And what does that give me?
6,300 degrees.
Woo! 6,300 degrees. That's right. Very good. Home plate in baseball has 3 right angles and 2 other congruent sides. What would be the measurement of those 2 other congruent sides? So this is sort of an extension of what we've been doing already. It's a pentagon, right? What is the angle measure in a pentagon? Close. 540, right? How would we find it? Well, we would take n minus 2, that's 5 minus 2 or 3, times the 180. If you didn't remember a specific one, right, that's the formula, you can use it. So this is 540 degrees. How could we use that to find those missing angle measurements?
You could do 540 minus all your right angles.
All right, and how many right angles do I have, Amy?
3.
There are 3 right angles, so I can do 3 times 90, or I could do just subtract the 90 3 times. Okay, so those are the angle measures that I do know. There's 3 of those, the top 2 and the very bottom one. What does this give me if I take 540 and I subtract 270?
270.
Is it 270 left over? Awesome. So then what would I need to do with the 270 to find the angles that I'm wanting? I would need to divide by 2 because they're congruent. It told us that. So what is 270 divided by 2? 135 degrees. It's a physical object. You've probably all seen one at some point. It's 135 degrees in those 2 angle measurements. We can actually go the other direction as well. If we know the sum or we know the individual angle measures of a polygon, we can figure out how many sides the polygon has. We do need to know that it's regular for what this particular problem is going to ask us to do. It tells us we have a regular polygon, and the measure of each interior angle is 162 degrees. So I don't know how many sides are in my shape. It should be regular, so all the side lengths should be the same. Okay, that's a terrible picture. Just pretend for a moment. So all of these angle measures are the same, and I'm trying to figure out how many sides my shape has. So, any ideas about what I could do? I have a wonderful formula that I might be able to use if I manipulate a little bit. The formula said that n minus 2 times 180 gave me what?
Number of degrees.
Okay, the number of degrees in what? Okay, so I'm going to call it the sum of the degrees. Is that okay? Or the sum of the angle measures. That's even better. Now, we do not know what n is. That's what we're trying to figure out, right? We don't know what n is. How could I use the information I am given to find the sum of the angle measures?
You could put 162 degrees in after your equal sign.
So where did 162n come from, Amy?
Each interior angle is 162 degrees.
Okay. So if n is my number of angles, then I can take my number of angles, n, times the angle measure, 160. Right? That's what we would do if we had a square. That's what I just did on this problem over here. I had 3 angles that are all 90. Right? So now I have n angles and they're all 162. My other side of my equation, I can actually do a little bit of algebra and distribute. So this is 180n minus what? What's 2 times 180? 360. Exactly. And then I could subtract my 180n to the other side, just to get the n's together. So what happens if I take 162 minus 180? What's that? I get a negative. That's okay.
It's negative on both sides. So you
Yes,
get rid of it.
exactly. There's a negative 360 on the left. What do we get on the right? Negative what? 18. 18. 180 minus 162 is 18. And then what would I do? Yeah, so then I'm going to get rid of that negative because I'm dividing by it, okay? So I've got a negative divided by negative. That will be a positive. So my n value equals what? What is 360 divided by 18? 20. So this is a 20-sided polygon. Okay, we just have a couple of more slides to go through, so let's move through those quickly. The exterior angles of a polygon, they're the ones that are highlighted in blue. Okay, we've talked about this figure before. We talked about it last class period. These blue shapes right here all add up to 360, and it doesn't matter what the polygon is. Always add up to 360. Okay? So that's a feature that we're going to be using later. All right, this is our actual last example. And what we're told that lines A and B are parallel. We have the top angle that's marked in pink that says 135 degrees. The bottom angle marked in pink, it says 140 degrees. And this angle that we're looking for over here is x. And we're supposed to figure out what is x. There's multiple ways to do the problem. Because we're running out of time, I'm going to show you one of them, okay? Any thoughts that you guys had when you see this problem on what you might try? Elena?
Draw a line between connecting line B and A. That way you create a polygon and go from there.
Fantastic. So where would you like me to draw such a line?
Right before the arrows.
Okay. So over here? How do you want me to draw the line? Like this or like this? What would you like me to do?
Completely straight.
You want it to be straight up and down. So in other words, you want it to be perpendicular. Why might that be helpful? It's not the only way to do it, but why are you thinking about that way to do it?
I know the angle measurements.
Yeah. And even if you don't know those angle measurements, what can you tell me about those angles even if it were on a slant? Do you know? They'd still add up to 180 even if they were slanted. Okay, we haven't actually encountered the reasoning exactly behind that, but it goes back to these alternate interior and exterior kind of angles. What shape did we create then? Pentagon. And just for the record, this is a fantastic way to do it, and it may not be the same way that you thought of. Because when I created it in my mind, I created a triangle. I drew that vertical line that Elena had us draw, and I drew it actually connecting that 135 down to 140, and I did it a little differently. This image, though, is a little bit nicer looking than my triangle, actually. So how many degrees are in a pentagon? 540. So what then would I need to do? Oops, look my zero there. I would need to take away all the values that are here, right? So that's the 135, the 140, and 290s or 180, right? You can either add those all together, that's what I actually heard a couple of you say, and then subtract them from 540, or you could subtract them one at a time from 540. That would be okay as well. What do you get? 85? Do I have a second on that? What'd you get, Elena? I have something else written down, but mine might be wrong too.
My problem was set up differently, sorry.
That's okay. Did I get all my values in the right place? You got 65. So we've got a possible 85 and a possible 65. Just for the record, my paper actually says 75. Sort of halfway in between y'all. So somebody grab a calculator just to be sure.
85.
Is 85 right? Awesome. 85 sounds good to me. So we have 85 degrees for the missing angle x. If you do it with a triangle, let me just say real quick, and then I'll let you go. If you do it with a triangle, and if I had drawn that straight up and down like I intended, we'd have this 90 here and this 90 here. Well, I've got a triangle over here, right? You know triangles are 180 degrees. Well, how would I find these angles here and here? What'd I do?
90 subtract 140 and then 90 subtract 135.
Yeah, I'm going to say it in the other direction, Elena. But yeah, we're going to take 135 minus 90. What's 135 minus 90? I think it's 45. Yeah, that's my problem. I didn't write that down right on my paper. And then I do 140 minus 90. What's 140 minus 90? 50, right? 50. So then we could do the same thing we did with our pentagon, but we could do it with a triangle. So we do 180 minus the 45 and the 50 to get 85, either of those ways. All right, fantastic. Good job, guys.